Actually, in the last class, I think we were discussing various coordinate systems, celestial coordinate systems, and two systems we discussed. One was the most commonly used one, like a horizontal system, which is nothing but the observer and the horizontal plane, vertically above is zenith, and that is the most obvious choice because of the observation is done in that way. So therefore, but the problem of that is that it is dependent on the observer's position. So the coordinates, etc., whatever you decide about the planets and the other objects, they are not something which is absolute, but they are all dependent on the observer's position. So therefore, it is always necessary to convert those coordinates to other systems which are independent of the observer's location. So in that, the first system was this equatorial system, which was very similar to Earth's system. That means the celestial equator is there, and there is a chosen preferred meridian. That is, of course, arbitrary. In the ancient time, it is to pass through J, but nowadays internationally accepted reference meridian line, it passes through Greenwich. Anyhow, so you can measure the two angles along the equator and perpendicular to that in a direction towards north or towards south. So one is called right ascension, the longitude, what we call in the terrestrial system, and the latitude is called declination. Inclination, the declination is positive when it goes to the north, and it is negative. There is another very important system which is suitable for more scientific investigation is the ecliptic system. The ecliptic system is like this, which I have shown here. You can see this is the Earth's this is the axis about which Earth is spinning, and this is the equator, celestial equator. But the ecliptic, which is the projection of the ecliptic plane onto the celestial thing, on which sun is always there, all the planets are mostly around that, not very far away, because this represents the orbital plane of most of the planets, slightly tilted. That's why they're not exactly on the ecliptic, but it changes little, slightly. And here, this is another kind of pole. You can see this pole is actually on the celestial dome, where the line passing through the center of the Earth and perpendicular to the ecliptic plane, and that is called ecliptic, which is very significant astronomically. But for us, observation point of view, it is the celestial pole where the axis of the Earth, its extension or projection, is the celestial dome. Where currently we have a star, we call it Polaris, Dhruva Nakshatra. So now I think here there are again two angles. One is along the ecliptic, just like the equatorial system. Along the ecliptic, suppose this is your object, which you have to fix its coordinate. So you start from a reference point, and this angle is called longitude, represented by the symbol lambda. And along these are also another kind of meridian line, which are connecting the ecliptic poles. Along that, we call it latitude. Here the language is, or terminology is exactly same as what we find in the terrestrial system. The longitude is the angle which you go along the ecliptic, and the latitude is the angle when you go perpendicular. So now the question is that which is the reference point? Now traditionally, the Western system has always used the vernal equinoctial point as the starting origin point. So this is the 0-degree longitude. It is our y-axis. If you consider it to be similar to xy, then this is the x-axis, and this is the y-axis, your 0-degree length. So this is the reference point, and the angle is measured from that point along the ecliptic, which is called the longitude. And latitude is positive if it is towards north, and it is negative if it is towards south. Now the question is what you will say that we have already discussed, that because of the precision of the equinox, this equinoctial point, intersection of the equator and the ecliptic, slowly shifts towards west along the ecliptic at a rate of approximately 50 arcsecond per year, or 1 degree every 72 years. So how can we take this as a reference point? So if you decide the longitude to be something, after a couple of hundred years, the longitude will be different because it will be more, because this has shifted towards the west to some other. So longitude is not a constant thing over large periods of time according to the Western system. Indian system follows a slightly different procedure. They start the reference point is a fixed point on the ecliptic, which is taken in Indian system is the first point of the RES or Mesh Rashi Prothom pointer. There are 12 Rashis, so they divide the whole ecliptic into 12 regions. The beginning of the Mesh Rashi, that is taken as the reference point in Indian system, and that point is called Meshadi. Adi মানে starting point. So Meshadi টা হচ্ছে গিয়ে Indian system, and that is fixed, that never changes. So therefore the longitude in the ecliptic system, there are two types of longitude. One is called Nirayana, that is the Indian system, which does not change with the ion. Ion means equinox, precision of the equinox. So Nirayana is the Indian system, and Sayana is the Western system, which is obviously dependent on the ionochalan, that means the precision of the equinox or movement of the equinoctial point. So these are the two types of systems which we have, and when we discuss Indian astronomy, we will again bring out these points. But keep it in mind, there are two types of longitude. One is Sayana, that is the Western system which is followed, and the Indian system is called Nirayana, which starts from the Meshad or the first point of RES sign, and the Western system starts from the vernal equinox. So this is another system which is, again you can see that for our many scientific purposes, like say if we consider astronomy, where we try to figure out how old a particular description is, there this ecliptic system is more suitable, because we can find here the change in the longitude time, because it is dependent on the precision of the equinox. So this ecliptic system is also a system which is independent of any observer position, and in Indian system the latitude longitude of a particular object is fixed, it never changes in case of the fixed star, and in Western system the fixed stars also their longitude changes over time, because the starting point shifts along the ecliptic towards west at a rate of 1 degree every 70 years. After say 1400 years, I think the longitude will be more by 20 degrees. You measure it today. So that's so this is what I have written here, that the first point of the sign RES, that is Meshadi, that is our reference point in terms, and Western, that is called Nirayana longitude, and the Western system is Sayana, because it takes care of the precision or the shift of the equinoctial. So the symbols used for the latitude is lambda, and it is always measured towards east, and the longitude or latitude is presented by sign beta, Greek symbol beta. It is positive if it is towards the north ecliptic pole, and it is negative if it is measured towards the south. Now you can see that the two systems, for example, the celestial equator, and this is the eclipse. So this symbol is generally used for vernal equinox. You will find standard symbol. So if an object is here, So the longitude will be from here, this angle, lambda. This will be lambda s, which is Cheyenne longitude. And this is the beta. This is beta. Beta is same in both the cases because it is measured from the ecliptic. In Indian system, it is the Meshadi point. Why it is here? Because when Indian system starts at Meshadi, then at that time, in 2000 years, this has shifted towards west. Why it is somewhere here. Originally, they are more or less at the same location. So this being the starting point of the Mesh Rashi, Meshadi, this is the Nirayana longitude of the object star here. This is the Nirayana longitude, lambda n. It is written here as lambda t. I don't know why they use t. So red one is the Sayana and green one is the Nirayana. Longitude, latitude will be same in both cases. And this difference, this amount, when you want to combine both the Indian and the Western system, then you have to take care of the Sayana longitude by adding a quantity which represents the shift of the diurnal equinoctial point and which is called Ayanansha in Indian system. So, if you add Ayanansha at a particular time, then you get or you can convert the Sayana longitude, Nirayana longitude to Sayana longitude. It's very obvious, you can. Now, I think next thing what I think we have to discuss that how do you transfer? As I mentioned, the most obvious observational coordinates will be the horizontal system, which depends on the person concerned or the location of the observation. So it is essential to make a real, but you cannot make a long time analysis unless you go to some coordinate system which does not depend on the location of the person. Not only the location, it also sometimes depends also on the day of the time or the period when you are doing it because Earth is rotating. So therefore, this is very important and that is done by the transformation of the coordinate from one system to another. But before that, I think what I would like to mention for that, what we have to do is we have to understand a little bit of now. Don't be concerned about this. That trigonometry it sounds highly mathematical, but very simple thing which will go will you will see that it is absolutely high school level material, and that's why I would request you to be a little bit attentive here. Now, so this brief introduction to spherical trigonometry, I am saying it is essential not only for transformation of the coordinates, but also to understand the rising and setting points of the stars and planets, heliacal rising of stars and constellations, and then only you can tell that a particular time of the day, at a particular year, at a particular latitude, at what point sun will rise, or at what point sun will set, or a star will rise. To understand that, you have to have a slightest knowledge what is required in spherical theory. Actually, spherical trigonometry also is not very different from the regular plane trigonometry, but I think since it is not discussed in school level, I would like to discuss it and derive the most fundamental basic relation which will be used by us. Now here the celestial sphere and spherical trigonometry. Now, as mentioned earlier, the sky, along with all the heavenly objects, appears as a celestial dome because you can't have the depth perception because all objects are at extremely large distance. So our the separation between two eyes is so small compared to that we don't feel any depth. Actually, in the normal case, we get a feeling of depth only because we have two eyes, we have binocular vision, and we have the distance between two eyes that makes the depth perception. But in case when the distance is too large, our eyes to eyes fail to gauge the depth. So it looks as if everything is plastered on a particular spherical dome, and that's what we call celestial. The relative alignments and positions are all described on this imaginary sphere. It's not a real sphere, called the celestial. On a plane surface, the coordinate systems are developed using straight lines. Like for example, in a plane, how we do it is standard practice is to use two straight lines. This is the x-axis, this is the y-axis, this is the origin. How do we fix up the position of a particular point? We can say that this is a particular point you have to fix up. The easiest way is to find out how much you have to go along this, which we call x, and how much you have to go along the other perpendicular direction, which we call y. So the two quantities x and y completely specifies the location. That you all know from your even I think early school days. Now similar pattern is used in case of spherical trigonometry, but there we have to do it on a spherical surface, not a flat plane surface. So we have showed that it is done with the help of straight lines. X is one straight line, y is straight line. Now I think we should remember in all astronomical observation, only thing what we see is the direction in which an object is seen. We don't know a position or anything is not. Only we see it is found in that direction. Remember, that is the only thing which is visible or possible in observational astronomy. Thus, the distance or separation between any two objects in the sky is nothing but the angle between the two viewing lines. Suppose object A and object B, so the only difference will be the angle between the two. On a spherical surface, so this is the celestial sphere. We are here, Earth. This is one object and another object. We can only see the direction in which these two objects are seen, and this angle is the only thing which you can measure, and that describes the distance between these two objects. Angle, nothing else. So in spherical trigonometry, you will find angle represents everything, and that we will again mention, and we will see that. So this is what I just now showed, that this is the Earth, North Pole, South Pole, and and this is the celestial dome, again the poles. So these are the meridian lines, as you see. But when you see from here, Earth, this object will be seen in this direction, and this object will be seen in this direction. So the distance between the two is nothing but the line or the angle. Now this angle has got, this is the only thing we can measure. But what is this? Now this depends also on the radius, but that we don't know. So therefore, this distance also is represented by the angle. Remember this. So in spherical trigonometry, distance between two points is also nothing but the angle, which is subtended by these two objects from the center of the sphere. This is a very important point. In case of plane trigonometry, the whole trigonometry, it is nothing but properties of triangle. So what we do in plane trigonometry, we take up a triangle A, B, C. You are all familiar with triangle. Now how a triangle is constructed? Triangle is constructed by three straight lines. This is one straight line, this is another straight line, this is another, and they form this triangle. So what forms a triangle in spherical trigonometry? Again there you will see that in spherical trigonometry, a triangle will be like this: A, B, and these are the three sides. Now the question is, the side lengths are A, B and C. In spherical trigonometry, the symbol which is used for representing length is always in lowercase. So, now the question is, which says that in plane trigonometry, we form a triangle by three straight lines. What is a straight line on a spherical surface? That is the first thing we have to resolve. That's what we will do now. What is a straight line on a spherical surface? Now, two triangles are shown here. One is a regular plane triangle, as I showed, and another one drawn on the spherical surface. Now, three straight line on a plane surface is very straightforward, as you can see, and we can, all this length as A, this length is B, or H is the hypotenuse, is one side of the right angle triangle, and in trigonometry, the basic relations are derived with the help of a right angle triangle. A right angle triangle means this angle will be 90 degrees, the horizontal line and vertical line, and this is the hypotenuse. So therefore, it is the Pythagoras theorem of a right angle triangle that decides everything. And this angle may call theta, and we will have the definitions using this theta. So, to now find out that when you draw a triangle like this on a spherical surface, they have to be straight lines, equivalent of straight lines on a spherical surface. So, their first thing will be, what is a straight line on a spherical? That we have to do. Now, you see, in case of plane, like say, when you consider a straight line, how do you define a straight line in the normal plane surface? This is a point A, this is a point B. How we define a straight line? You know that it is the locus of a point. If you go from here to here, which will be the shortest distance. So the shortest distance between two given points is found by joining them by a path, which is called a straight line in the plane. So the same kind of definition is used to define a straight line on a spherical surface. So this same approach is defined or used to define a straight line. So let us see this. So this is a spherical surface, and A and B are two given points. You have to find out the path along which the distance traveled between A and B will be short, and we will define that as a straight line in the case of a spherical surface. Now, what are these lines? Now, I am not going into the proof, but I will just tell how it is found. This path is found by considering a plane. The plane will be containing, to define a plane, you need only 3 points. This point A, this point B, and the center of the sphere. If you take this plane, imagine that plane, and the path or the intersection between the spherical surface and the straight plane, that will be the path. Now, what is this circle? This will be a circle. You take any plane and you pass it through the center, it will give a circle of the largest possible size with that sphere. If you take any other plane, I will show you this. You have a sphere, spherical surface, and you consider a plane like this, and it will cut it like this. You draw another plane, will cut this. But if this plane passes to the center of the sphere, then, okay, so this is the sphere, the circle, which will be produced by intersection of this plane and this, if it passes to the center of the sphere. And this circle will be the largest possible size of this circle you can generate by intersection of the plane and the sphere. So, we have seen that we can get a circle by intersection of a plane and that spherical surface, and that circle is of largest size if the plane passes through the center. These circles are called great circles. And when a great circle connects between A and B, this distance will be the shortest. It can be mathematically proved, but I'm not going to that proof. Okay. So now, but the length of this line, how do you define this length of this straight line or the great circle? That is done by the angle. So this angle that defines the length. So this is the great circle. So therefore, we have seen, I will show you in case of Earth, for example, if you want to find out the shortest between two positions, say Vancouver and say Paris. Now, if you consider the great circle and the path which is generated by that, it will look like this in a normal map. Many of you who have flown in international flight, you have taken, and in front of you, it is shown that what is the flight path. It looks like a curved path, and many wonder that why are you not taking this straight path like this? But that is not the shortest distance. The shortest distance is this one. Intersection of the plane joining these two positions and the center of it. So therefore, in the typical map, the longitude lines appear to be straight. They do not represent the shortest path along the spherical surface. It is not the longitude, it is the latitude line. I'm sorry, correct it. This is not longitude, it is the latitude. Longitude lines are actually great circles and they represent the shortest. But the latitudes are not the great circles. So they don't represent the. So therefore, if you take the latitude circle, which will be like this, its projection, that is not the shortest. It will be this one, which is the intersection of the great circle or the great circle passing through this position. So now I think that is, so therefore now the first thing what we had a problem, how to define a straight line on a spherical surface, that we taken care of. That means the straight line equivalent on a spherical surface is a great circle. So please correct this also. Co-stop, make it latitude, not longitude.
Okay, sir, I will change it.
Yeah. So I think that point taken care of. Now we can proceed to find out the relationship. What is done in normal plane trigonometry is the relationship between the three sides. This is the one, this is called B, this length AC, and the vertical line is called A, it is BC, and the hypotenuse is called C. Now you will see that the symbol used A, which is opposite to the corner A. Symbol is B is opposite to the corner B, and symbol is C to represent the length of the hypotenuse is against opposite to C. This same kind of methodology we will follow in spherical triangle, spherical pyramid. Now, what are the basic definition? If this angle is theta, then the ratio of this BC divided by AB, that is small a by small c, is defined as sine theta. That's definition. That's definition. And the ratio of the horizontal, that is this length B, and the hypotenuse C, is called the cosine theta. So it is quite clear that since hypotenuse is the largest in a triangle, right angle triangle, these quantities will be smaller than 1. Unless this angle begins to become 0, then C will almost come here. So this A will become 0 and B will become equal to C. For cosine 0, this is 1, sine 0 is 0. So these are the similarly, if it becomes 90 degrees, then obviously you can see that there is another problem. That means cosine will tend to become 0, and A and C, they will be equal but very large. So that ratio will be equal. Now another thing you see that by Pythagoras theorem, sine square theta, that means A by C whole square, plus cosine square theta, that is B by C whole square, is nothing but A square plus B square by C square. Now Pythagoras theorem tells A square plus B square is C square, so is equal to 1. So sine square of a particular angle plus cosine square of that angle is always. Another definition is done, which is derived from here, that the ratio between A and B, A by B, which is called A by B, which is called tangent of theta. You can see tangent of theta is nothing but sine theta by cosine. Now, another necessary formula which we'll be using in trigonometry, this is the only trigonometrical formula which you have to derive. That is this one. If there is a triangle A, B and C, and the angle between AB and AC be theta, then the length BC, that is opposite to theta, can be found out in terms of AB length, AC length and this theta. How it is done? Let us draw a perpendicular from C point to AB and this point. This is perpendicular, so this angle is 90 degrees. So, how much is BC square? Now, this is a right angle triangle, BDC. So, BC square is nothing but BB square plus CD square, CD square plus BD square. And with CD square, again you consider this right angle triangle. So, this is the hypotenuse. CD square is nothing but CA square minus AD square. So, this is BD square, CD square we replace by AC square minus AD square and plus BD square. So, this is AC square plus AB square minus AD square. Now, you can see that that BD is nothing but AB minus AD. So, if you use that AB minus AD and all these things, then just algebraic manipulation, the whole thing becomes AC square plus AB square minus 2AB into AD. AB into AD. Now, AD is again, you can see, is nothing but AC cosine theta by definition here. This length is nothing but C cosine theta. B is nothing but C cosine theta. So that means this is nothing but AC cosine theta. Okay. So this becomes therefore finally AC square plus AB square minus 2AB into AC into theta. This is the relation we will be using. This is a common relation, but still many of you may not remember it from your high school days. Write it. This is the only formula of plane trigonometry which we will be using, and of course these are the basic definitions and Pythagoras. These are the only two things which we will be. Now, let us consider a spherical surface, and let us consider three great circles. This is one great circle, this is another great circle, and this is another great circle. The three great circles, they intersect and you form a spherical triangle, ABC, like this. The nomenclature is that this is the AB. Suppose this is AB, is CA. So CA length is nothing but this angle it subtends in the center and represented by a small letter B because it is opposite this cone. This length C between the AB we call C because this is point C, represented by a small letter C, and this is nothing but the angle. And of course, similarly, BC also you can call it as small length is nothing but this angle here, and so this is the basic nomenclature. Now I think these are the angles subtended by these arcs, the center. But you can see that there are other angles which are formed. If you take a tangent from here to this great circle and tangent to this great circle, they make an angle, sorry. They form an angle, and that is a normal angle, and we call it capital A. Similarly, here you draw a tangent here to this great circle, tangent here to this great circle. Angle between the two tangents is angle B. Now it is also not only that, but the plane which is producing this great circle and the plane which is making this great circle, it is also the angle between those two planes. So these are the other kinds of angles. These angles are the corner angles, and they are represented by capital letter A, B, and C. So these are the symbols which we use and the formalism. So length are represented by small letters. Angles, corner angles are represented by capital. So this to I think just if you this angle thing just a little bit more I would like to mention. Say this is the spherical surface. You have a great circle here, another great circle say here. So here you draw two tangents, tangent to this great circle and tangent to this great circle. This angle is the angle say A. So therefore this should not be confused that small, whenever you find an angle represented by lowercase, remember it is nothing but the equivalent of a length of a side of a triangle, and capital letters are used for making this kind of regular angles at the junction points between two great circles. This is shown here so that there is no confusion. This is a spherical surface. These are two great circles. This is one and this is one. So the two tangents you draw at this point, and the angle between these two is a normal angle, which is the angle between two great circles here. On the other hand, that a particular length along a great circle, the angle it subtends at the center, that is considered the length of this. Now I think let us derive the important fundamental relation of a spherical triangle, the angles, corners, and the angles of the lengths. Now I think let us consider, without losing any generality, let us consider this situation. Any particular spherical triangle can be configured like this. This is the sphere. This is the sphere. Now there are three great circles. This is one great circle. This is another great circle, and this is another great circle. They produce this spherical triangle. So this bottommost position we call A, this we call B, and this point is called C. And therefore this length or this side is called small a, this side is small b, and this side is small c. Now if you draw the angle, regular angle, which are nothing but the tangents of the two great circles, we call this capital A angle, and the other also we will see. But now currently we need only this kind. Now draw or a line joining the center of the sphere and B point, extend it. Similarly, join this with C and extend it. And imagine a plane touching the sphere at this point. So there is a plane. So therefore, if I draw it, this point, this is the plane which is touching point A. This plane, a regular plane, and this point I have joined this center with this. So you extend this line, it goes and meets this plane here. We call it D. Similarly, you extend this, and it goes and meets this point here. Call it E. Now join these. Now you notice few things. So this center O and this point O, it is the radius of the sphere, and it is touching this plane. So therefore, any line on this plane and this, they must be at right angles. Similarly, this is the radius and this is the plane. A line on this plane and the radius, they must be also in right angles. So therefore, this is a right angle triangle. This is a right angle triangle, and this ADE is a regular triangle, normal triangle. So we'll use these properties of normal triangles for this, this, and this. That's what we are doing. So therefore, what I showed, that we join the center of the sphere with this point B, extend it, and it meets the plane which is touching at this point A at B. Similarly, this line. So this is a right angle regular triangle, and this is a right angle regular triangle, and this is a regular triangle with this corner angle E, capital A. And the side length, that means this C is nothing but the angle this subtends here. A is length is nothing but the angle between these two lines, and B is nothing but the angle between, by definition. Now, so therefore, what happens now, that if you remember that figure, now of course here you have to, better that you also draw that figure, so that it will be, because I have to otherwise go back and forth, I don't have the figure. You will find that DE square, that means what is DE? DE is this line, this line. So best thing will be that if I use this, how much is DE square? The trigonometric relation we derived, this square plus twice this into this angle. So it is AD square plus AE square minus twice AD into AE into cosine of angle A, capital A, remember this. Okay. This triangle, if you see, then you can have two more relations. The OD square will be equal to OA square plus AD square. Similarly, on this side, OE square is equal to OA square plus AE square, because they are right angle triangle. This is 90 degrees. So these are the relationship we have. First of all, this angle C is what? Angle C is, as you can see here, according to the definition, angle A is BOC, that arc. Okay, the angle B is angle AOC, which is subtended at the center. Angle C is the subtended angle at the center. These are the three sides of the spherical triangle. Now, the plane defined by this triangle, that is ADE, which is touching this sphere, the point A. So, according to the definition of spherical angle, it is given by this angle is the line AD is the tangent to the segment, and AB is the line, A is the segment to the face. So, therefore, it is also obvious that in triangle OAD, angle OAD is equal to 90 degree and this is 90 degree. C, therefore, AD is equal to OA tan C by definition. And one thing, sec is nothing but 1 by cosine, a definition. So you can see that Actually, OA is equal to OD cosine C. Similarly, AE is equal to OA tan B and OE is equal to OA sec, or OA is equal to OE cosine B. Using this, and this is the relationship which I have just now written, and we derived this relationship at the beginning of the class. Now this, whatever we have just now find out, we replace AD square, AE square by these two quantities, and you, in terms of OA, you get. So therefore, this plane triangle, again, equal to, as per definition, we have seen this. Again, this is the relationship, which is nothing but. So we finally get, by equating the two dE square obtained by the two approaches, you get tan square C plus tan square B minus this equal to 6. Since DOA is an angle A as per the definition of spherical triangle angle, so therefore the above equation can be rearranged. These are all just simple high school level arrangement. Cosine A is equal to cosine B into cosine C plus sine B into sine C into cosine A. Now this is the fundamental relation you have to remember. We will use only this relation for all cases. What is the relation? The cosine of an angle or of a side A, which is angle represented by side A, is equal to, you can see A, and this is cosine B, cosine C. So it becomes A, B, C plus sine B into sine C into cosine capital A. Just remember this formula. It is the fundamental formula. All other spherical trigonometric formulas are derived from this. So therefore, the basic ratio, similarly, you can have a similar relationship for cosine B, a similar relationship for cosine C. Okay, by the same procedure. But the procedure will be same, but the relationship will be like this. Cosine A is given by cosine B cosine C plus sine B sine C into cosine capital. This is the corner angle of the sphere. So therefore, to find out the length of a particular side A, you need only the two other sides B and C and one angle, which is the regular, the corner angle A, opposite to the. That will be all you need. Now say, I'll just give you an example, the application of this on Earth's surface, because it will be easier for you to understand if you do it on Earth's surface. But basically, it will be the same if you do it for the heaven or celestial dome. What we will do here, let us find out the distance between two cities in USA. One is Los Angeles, which is B, and the other is New York, which is C. What is the distance between the two cities given their latitude and longitude? So the positions are given by latitude and longitude. Latitude of Los Angeles, longitude of Los Angeles, latitude of New York, and longitude of. Now remember that what is latitude and longitude? Now this is the equator. This is the equator. So therefore, the angle which you get from the center of the Earth and point B and this is the latitude, this angle. So this angle will be what then? This is the angle subtended center, 90 degree minus this. So 90 degree minus the latitude gives, we join this pole, North Pole, with the help of a great circle. With the help of another great circle, I join New York. They are nothing but the meridian lines. The meridian lines are the great circles. So this is one great circle along the meridian or longitude line of Los Angeles. This is the another great circle line, which is along the longitude line of the New York. So therefore, what is the angle A between the two? Can anyone tell? This is the longitude circle or the plane which cuts the sphere of this earth and the plane which cuts the sphere along these two directions. So what is this angle A? Angle A, you can easily see, is nothing but the angle between the two planes, two meridian planes. And what is then that? which is nothing but the difference between the longitude of the two places. So, the capital A angle is nothing but the difference between the longitude of B and C. That is decided. Is there any problem? I will explain again, maybe better. But if there is no question, I think we will assume that you have. So, angle A, corner angle A, is the difference between the two longitudes B and C. So, since the longitudes are known, capital A angle is known. Now, how much is this B, length B? Length B, we have to find out A, remember that. A is the distance between B and C. That is what we have to find out. Now, what is given? Capital A we have found out because it is nothing but the difference of the two longitudes. And what is side B and side C? Now you can see angle C, which it is subtended at the center, is nothing but 90 degree minus the latitude of B. This is the center of the Earth. This is the North Pole. This is a meridian line, and this is the equator. So if this is Los Angeles, what is this angle? Is nothing but 90 degree minus latitude of Los Angeles, so theta LA. Similarly, New York, what is this angle? This is called C, this is called point A, this is called B, and this great circle is A. So C is again nothing but 90 degree minus latitude of New York. Angle B is 90 degree minus latitude of LA. And capital A, this angle A is nothing but longitude of, or say longitude is this, say LA minus longitude of New York. Because 0 degree longitude is somewhere here. So this is the longitude of New York and this is the longitude of LA. So this angle is nothing but this minus this. So therefore now we have at our disposal most of the things. We know how much is B. It is 90 degree minus latitude of New York. Angle C, or C is equal to 90 degree minus latitude of this, and the angle A is the longitude of LA minus longitude of New York. So therefore now we can use that formula to find out how much is A. So latitude of Los Angeles longitude is this, and this is the longitude and latitude. This is the longitude 118.2426 degree west because it is west of Greenwich, and 34.0549 north because it is above the equator. Similarly, New York longitude is little bit less because it is nearer to Greenwich, 74.006 degree west, and the latitude is more, it is 40.712 north. So the corner angle A is the angle made by the two longitude planes, that is A is equal to the difference between the two longitudes, 44.236. And the triangle side B is co-latitude of New York. What is co-latitude? 90 minus the latitude. So that is this. And what is this triangle side C? Co-latitude of LA, that is, which is 55.9. Now the task is to find out side A. Use this formula, cosine A is equal to cosine B. Eke dakche. Cosine B into cosine C. Mina, somebody is calling. Sine B cosine C plus sine B sine C into sine capital A. Now substituting the values for B, C and capital A, you can just calculate and we get cosine A is equal to this. And from that we can find out A is equal to cosine inverse. That means cosine of A is this much, so A is cosine inverse this, and the angle becomes 36.5247 degrees or 0.6375 radians. This is the natural angle, you all know. Now, to get the length of this great circle segment connecting LA and New York can be found out by multiplying this by the radius of the earth, average radius, which is 6371 kilometer. And so this distance AB along the great circle becomes 4061.5 kilometers. So I think that's what I wanted to show one example, because I just derived something and how do you use it, that is one way. But I think that's an application of these spherical trigonometric relations. That's what I wanted to show you. The similar, as I mentioned, that we had the relation for A, cosine A. A similar relation for cosine B you can develop. The easy to remember this. It will be always the cyclic way. So cosine A, cosine B, cosine C, sine B, sine C, sine A. Here it will be cosine B, cosine C, cosine A, sine C, sine A, and cosine B. Similarly, cosine C will be cosine A. So it will be the cyclic way. A, B, C will be always in a cycle. And only thing, last one will be capital. And some other relations can be always derived, which we may not require now, but later when you do the conversion of the coordinate systems from one system to another, then we may use these relations. Sine capital A by sine small a, sine capital B by sine small b, sine capital C by sine C. They are all derivable from the three basic relations which you have derived. Nothing more is there. So this is called the sine formula, which is sometimes very useful. So like that, spherical trigonometry has various relations, but the fundamental relation what we derived was that cosine A is equal to cosine B cosine C into sine B sine C, and there are other kinds of relations. Cosine B, this is the cosine A formula, cosine B formula, cosine C formula, and this is called the sine formula. Using this, you can have other kinds of relations, but again, these mixing of these kinds of things are the only thing what is needed. So these are the basic relations which we will be using, and what I will request that please go through the very basic derivation, which is straightforward. But one example which I showed to show the application of spherical triangles is this. You can ask them to find out the distance between Bangalore and Dibrugarh. Okay, give the latitude, longitude, or you can say Melbourne and New Delhi. Find out the distance. So you can ask them to do it, and they will have a little practice of this spherical trigonometry, and that's all. We will not have any further need of spherical trigonometry until unless we go for the transformation of coordinate from one system to another. So I think next job is actually transformation of coordinates, which I think that's why you were deriving all these things, and also we will be requiring these relationships when you have to find out at what point the sun rises on a particular day of the year and at a particular latitude. Okay, so to do that, I think it is essential to apply the spherical trigonometry relation. That is one important thing. And I'm going to say, besides coordinate transformation, in two other cases, we will use the spherical trigonometry. One is the determination of the rising and setting points of the celestial objects, depending on the latitude of a place. And that means what will be the azimuth of the rising point, okay, in horizontal system. To find out that, we will need spherical trigonometry, and the heliacal rising. Heliacal rising is something which we may need only for archaeoastronomical purpose. So that I will discuss later when we discuss archaeoastronomy.